our whole global trade system was kind of enabled by tooling. And now we're going to remove tooling out of the equation.
Are you ready? All right, let's go.
Manufacturing is sexy. Sounds crazy? Just wait. I'm Z Holly, host of The Art of Manufacturing. Your behind-the-scenes look at how people who make stuff are trying to make it in their industries. If you've ever wondered how to build a brand, a business, or just a better mousetrap, tune in and enjoy. When people talk about 3D printing, what do you imagine? Do you think about those cheesy plastic parts? There's a lot of talk these days about how additive manufacturing is going to change the world. But it's hard to get excited if that means our world can only be primary colored polymer knickknacks. Recently, metal 3D printing has become more feasible, and it lets us create parts that can't be made with any other manufacturing techniques. But it still has its limitations. It's ridiculously expensive, it's dangerous, and it's slow. Desktop Metal is the 3D printing company that set out to change all that. They've raised $270 million to date, and their first product is a machine that everyone's talking about because it will print metal parts on the desktop. And they're about to launch a new production-level machine that will pump out parts as fast as using traditional manufacturing processes like casting and machining. The CEO, Ric Fulop, is an old buddy of mine from my days at MIT, so when I was visiting Boston a few weeks ago, I went to go visit and get a tour. And I sat down with Ric and two of his executives to learn more. We nerd out on their technology and what it means for the future of manufacturing. But what I was especially curious about is how metal 3D printing will change what we make and the way we design and innovate in the future. We hear about that and a whole lot more on this week's episode of The Art of Manufacturing. So, Ric, you were a venture capitalist. You're just kind of sitting in the ivory tower, able to just make tons of money. Why did you get back down into the fray of being an entrepreneur? What was the opportunity you saw?
I've been an entrepreneur longer than I was a VC.
But you knew better. Why did you go back into entrepreneurship?
It's so much more fun.
Yeah. But what was the opportunity that you saw when you were at Northbridge?
Yeah, the firm had been an investor in Proto Labs, and that was a great experience. And then we started looking at deals in metal printing. You know, I hadn't actually found a team that I got really excited about backing in metal that was actually working on the problem that I thought was kind of the biggest opportunity. And so decided to just go start a new company.
What was the need and opportunity that was not being met?
It's an offshoot of selective laser sintering. Some people refer to it as DMLS. Other people refer to it as SLM. But the summary is that...
But say what those acronyms are.
Yeah, so selective laser melting is SLM, and DMLS is dense metal laser sintering. It is basically welding with a laser, layer by layer, and you end up with very high resolution parts. It's also very expensive, and the powders are explosive, and they can't have any oxygen, and as a result, the machines end up costing $1 million, and you need special rooms. And so think of it as
slow.
They're very slow. It's
but besides that, they're awesome.
They're awesome. And they're great if you're making rockets, but they're not great if you're trying to basically do car parts or cell phone parts or, prototyping in your office, which is what most people do with plastic printers. So we thought there was an opportunity to bring metal printing process down to the desktop, and conversely, take our processes very slow, and at that price point, make it super, super fast and allow you to use materials that are 80% cheaper.
So what was the technology behind it that made this all possible? And what gave you the confidence that you could do it?
So we based the initial products that we're launching off of powdered metal technology, which has been around for 100 years. And in fact, it's people have been pressing and sintering functional parts out of powdered metal long before we were alive.
Chief Technology Officer Jonah Myerberg.
And actually that technology evolved into metal injection molding, where powder is mixed with polymers, essentially bound together, and then that bound powder is known as feedstock or MIM feedstock, metal injection molding feedstock, and that is injection molded into dies, and then complex geometry is created with those parts. And so we leveraged that technology in combination with 3D printing to basically remove the barriers of the mold, remove the tooling, and allow our customers to print basically any geometry that they like without the limitations of having to open and close a tool. And we do that two different ways. We have a studio system that prints those parts at your desk in the environment that the engineer works. It's an office-friendly system, the first office-friendly metal 3D printer ever in the world. And it's really been able to bring metal 3D printing closer to the engineer than ever before. So, allows the engineer to basically prototype at his desk overnight. But then what happens next? When the engineer qualifies a design and wants to move that design into mass production, he needs a tool to be able to do that. And so we've launched a production system. We call it the Desktop Metal Production System. And that uses the same metal powder, but we bind it in place. Instead of bulk binding and then printing, we bind it as we print it. And that turns out to be 100 times faster. And we utilize very high-speed 2D printing technology, stuff that's used in 2D inkjet presses. They're called digital presses. And they run at like 5 meters per second and print giant billboard-size images at very high resolution. So you put that in combination with printing binder on powder, and all of a sudden you have mass production of metal parts.
That's incredible. So how long have you been doing that?
So we've been doing that for about 2 years now. Since the company was founded, we were evolving these technologies, and we chose powdered metal as our path.
So how much does it cost for the two different systems?
The pricing for the studio, the printer starts around $50,000, but then you need a debinder and sintering system. So all in, you might be anywhere between $120,000 to $180,000, depending on how that gets configured. And then we have a production system that really starts around $750,000, but fully configured, it goes well above that. But that can make parts at anywhere between thousands of parts per day to tens of thousands of parts per day.
What are you the most excited about in additive manufacturing? What are some of the most exciting opportunities that you see, whether it's with your technology or others?
It's what's unique about the industry is that this industry is now to the point where the original core technology is starting to expire. So there's a lot of new open source that's coming online. So there's two classes of companies. Some are actually taking that open source technology and turning it into products that are sort of very affordable and mass market. That's happening in mass on the plastics side. And then what we're doing is working on new process development that's built on top of the original modalities where the patents are now open, and advancing the technology forward so that it can do things that the prior generation processes didn't do.
So it sounds like there's many different processes that you're using. At the beginning you described, and I think you showed two different approaches. One was the desktop model, but it's a two-step process.
The key thing that's different from the laser systems is that by separating the forming of the part from the thermal processing of the part, you're able to do it faster. You're able to use materials that don't have oxygen requirements, so you can use much lower cost materials, and you have a broader palette of materials that you can process because most materials are not weldable. So by not having a welding process, you can then use higher quality alloys or tool steels that are very high performance, materials like copper, et cetera. So that opens up the window.
So you could print all of those materials?
Yes.
That's incredible.
It is awesome.
And what Ric's hinting at is, metal 3D printing is not new, right? Metal 3D printing has been around for 20 years, but what has slowed the adoption of metal 3D printing has been exactly that, the process. And that process is how you described it earlier of welding the part together. And so what we did, as Ric described, is we separated the 3D printing process from the thermal processing process. So we print the part at room temperature, and then we put it in a furnace and we sinter it. Two separate events that happen and enable much more consistent, well understood properties.
There are so many benefits to 3D printing and additive manufacturing, but people may not know what those benefits are and how to take advantage of them. So a lot of it's in the software and the design tools, right?
Right. People realize that sometimes they make parts today that are overly heavy, and it's due to the manufacturing constraints. So if they have to start with a block of metal and machine it, or if they have to make a mold, they have to make sacrifices, and they end up with parts that are bulkier, or they're welded together out of separate pieces because they have to make them separately and put them together into the finished part.
That's Andy Roberts, the senior software engineer who invented their new generative design tool called Live Parts.
So they know they have these problems, and they usually come to us and say, well, let's take one of our existing parts and try 3D printing it. And we can do that and achieve success. However, we point out that these parts don't need to have straight lines. They don't have to have machinable surfaces or be fixturable or easily put into a mold or taken out of a mold. And they understand that, but if you look at mechanical engineers today, they don't understand how to build parts that take advantage of 3D printing. They're used to using traditional manufacturing techniques like machining, casting, sheet metal design, things like that, where they use their computer-aided design tools to manually create the features. So this is an evolution, and we start out with companies approaching us with the parts that they know well and they already have, and we 3D print them. But then we go through a process of essentially saying, hey, you don't need these surfaces here, or you don't need these shapes. They can be much more lightweight. So we develop software to help people create parts that are optimized for 3D printing. And the inspiration was, for us, from nature. We realized that people don't sketch trees or plants or animal bones, they just grow. So we came up with this idea that we could build a system of software that would model parts as cells growing into embryos and organisms, using the principles of nature for how cells multiply based on strain. So we've built this software that takes the constraints of the part and it grows the part to be optimal and strong and yet lightweight. The complexity of the geometry is very high. They look like bones or plants, and they're almost impossible to create using traditional computer-aided design tools, but they're effortless to create using the software, and they're effortless to print because we slice them layer by layer and print them no matter what the complexity is.
Let's see some of these parts. You have this ominous-looking briefcase over here.
Sure. So some of these first parts that we're going to show you are basically grown around constraint systems or constraint fields that Andy can describe.
Right. One of these parts is a brake pedal, and a brake pedal is fairly simple. It has a hinge at the bottom or a swivel point, and then a surface that you slam your foot into, and then it has an actuator that pulls on the master cylinder. It's different than with traditional design. In traditional design, you actually have to sketch and create the shape of the part. Here you do the opposite. You sketch and create the shape of where the part can't go and the minimal areas where it can go. And then you export this into our software called Live Parts, where we actually let the system grow the part to fit those constraints. So this brake pedal part here looks like a combination of some surfaces that you would expect to see from a computer-aided design tool, like the surface of the pedal, because that's something that has to fit to your foot. It can't have sharp, prickly edges to it. But the rest of it is free to grow pretty much how it wants. And so we get these natural sort of lattice exoskeleton shapes that grow strong. They don't have any hot spots where strain can build up or stress can build up, because where there's high stress, the cells naturally proliferate and grow stronger to diffuse that. So the part is naturally stress-free when it's grown.
And I would think environmentally friendly, and you're not using as much more material than you need.
Right. We have an idea that not only can we grow the parts, but we can also grow the support structures like a plant to grow up underneath the material where it's only needed. So you don't overprint material. You only print what you need. That's another benefit of additive, is that you don't start with a big hunk of metal that you're going to throw away 90% of the material. You grow only what you need, and the remainder of the material is used for other parts.
Cool. And what do you have in this ominous-looking briefcase?
So in this box, we have a number of metal parts, some of which have been grown with our software, and I'll show you a couple of those, like this little bracket.
Oh, wow.
This little bracket here. There are rings and mounting surfaces that are important for the application, but then in between the mounting points, it's really arbitrary what the geometry looks like. And honestly, I think that engineers have been designing parts in reverse, really, since the beginning days. You're really asking yourself, okay, where should I put material? And that often is not well defined. In fact, it doesn't matter a lot of times where you put material. Like Andy said, you want to talk about where you can't put material, where are the keepouts, critical interface surfaces. Define those and those only. And then the rest of the part needs to be strong. And it needs to, hold one surface relative to the other under certain conditions. This is an example of a lever arm So it has two mounting points that have a certain relationship with each other. And in between them, there are a couple of areas where you don't want material to be. And so right here, there's a head of a screw that kind of swings by that you want to make sure that the part stays away from. But otherwise, we don't really know what the geometry should look like. All we know is that it should be strong.
It's so funny because you're looking at it, it's like, okay, there's two rings, and then between it, it's just a bizarre, it looks like somebody spilled some solder or like left their solder iron like on the table or something. It's just interesting.
Right. And what in fact is going on is that we're using live parts, or Andy's software live parts is moving those two mounting rings relative to each other and growing material in between them. And that material is then stressed.
Like simulating the growth of this
That's
material.
right. And where the material is needed, it grows more. And where it's not needed, it withers away and dies. And you're left with a fully optimized geometric shape in between the two.
We had another guest on the show who's doing 3D printed cars, and they're doing the nodes that are using this generative design. So it's incredibly efficient with the use of the materials. And
I think I know that company.
Divergent 3D?
Yeah.
Yeah, Kevin Zinger.
Yeah.
Yeah, really interesting.
I drove in that car. The
Oh, yeah,
crazy
the Blade.
looking, the Blade, yeah.
Nice.
But the Divergent car is a great example of kind of taking this approach at printing big things, right? And their approach is that you print the mounting points, the junctions between the beams in a
The
frame.
complex parts.
The complex parts.
Yeah, and then
exactly.
they use carbon fiber rods for the.
Yeah, exactly.
Yep. And it's exactly the types of solutions that we're going to evolve as 3D printing becomes more and more.
We should actually call them and connect them with about live parts. They'd be a user of it.
Yeah.
It's like a perfect solution.
I'd be happy to make that connection.
Yeah.
You're listening to The Art of Manufacturing. Follow our adventures on Instagram and Twitter @ArtofMFG. And to chat with other like-minded creators, join the Art of Manufacturing Facebook group. We'll be right back after this break. The Art of Manufacturing podcast is a collaboration with Make It in LA, which is generously supported by organizations like the LA Cleantech Incubator. LACI has a really cool facility in the Arts District of downtown LA filled with energetic startups and nonprofits. They offer cleantech startups flexible office space, epic prototyping labs, and the #1 rated cleantech incubation program in the world. Learn more at makeitinla.org/LACI. We're speaking with Ric Fulop, Jonah Myerberg, and Andy Roberts from Desktop Metal. What's the challenge for you to be promoting using additive manufacturing for full production? Is there any pushback or?
No, I mean, it's people want to use it. It's always been about cost. And so the question is, what process are you displacing? If you look at 5 major processes to make parts, whether you're stamping sheet metal, whether you're using molds for castings, or doing metal injection molding, which is a different process. Are you doing press and sinter? Are you doing an extrusion? So I would say those are the 5 major ways you make metal parts. And what are you displacing? Because it's not like people can't make metal parts today. For a long time, people made parts, but they were essentially relying on huge engineering heroics. But today, with single pass jetting, this new technology, you don't have to do that. You could print any part less than 100,000, and it's going to be cheaper than casting. Our process for mass production is cheaper than machining, and it's cheaper than casting up to 100,000 units.
Amazing.
So that all of a sudden creates a huge market opportunity. A huge boon to this has been artificial intelligence and neural nets and things like that. So the techniques like what Andy's software does really can take advantage of GPU. A GPU is a graphic processor unit, which is initially invented for gaming. That means that you get in one single instruction set, you get more calculations. And so those have been adapted for artificial intelligence or self-driving cars, and now we're adapting them for CAD design. You know, you look at this really crazy pedal that's so organic. An engineer would never have come up with this design. And even if it did, this only took 10 minutes to build. Mm-hmm. So look at the productivity increase. Mm-hmm. It's less parts, way lighter, higher performance. It's got 10 times the stiffness sideways than the part it replaced. And all out of the same material. Before, they would have gone to carbon fiber, they would have gone to other things, but now you can keep it in metal. You make it better, And that's taking advantage of this revolution in GPUs, graphic power units, processing units, and artificial intelligence technology.
So for those that are either entrepreneurs or running a small business, they're not going to be able to afford $1 million machine. How is this going to impact the way they're manufacturing?
Well, the cost per part is going to be lower. So it's not like people go out and build a casting facility when they're going to do casting.
Now, do you have service bureaus that are your customers?
We have a whole variety of customers that are purchased our production systems, and when those are up and running, they'll be able to support the industry. And for large manufacturers in automotive and other industries that are at the scale, they're going to be able to do that themselves as well. So there is a combination.
And when do you think that that's going to be much more,
I would say,
common?
Common, I would say give it another 2 years, and that's going to be, you're going to have lots of options.
And how do I find the right service bureau? When is this actually shipping? When will somebody be able to buy the product?
The studio system is available now, and the production system is next year. We'll have some units in beta this year at customers, but it's limited.
It's interesting, this combination of speed, cost, and 3D printing, basically infinite geometry or unconstrained geometry has, as Ric mentioned, reached this tipping point in the industry where there's so much demand, where everyone wants in. And it's not new. Aerospace was the first adopters of metal 3D printing. They're really the ones who could afford it, along with the medical industry. But the automotive industry has been watching for a long time, and they've been wanting to get in and take advantage of the same things that the aerospace industry is taking advantage of. Complex geometry, parts consolidation. It's valuable to every industry. But our customers and sometimes our strategic partners in the automotive space are not ultimately going to be the ones who manufacture the parts. Right? Sure, they'll bring the technology in and they'll learn about it and they'll understand it so they can design parts.
Right.
But they're going to push the technology onto their tier one suppliers. They want their mass producers to adopt 3D printing as a manufacturing technique that they can then serve the industry with. So we call it service providers, right? So you have like a printing service provider who does your printing now for you. But in reality, it's the same as any stamping house or foundry house or high volume metal parts manufacturer. And that's ultimately what it's going to turn into. It's not really a 3D printing service provider anymore. It's now going to be open for any metal mass producer to adopt.
Feels, though, that if it were such an obvious slam dunk, then I could just go and raise $10 million, go and get 10 of these machines and just open up a service bureau. But there's some hurdles in the design, getting people to understand how, right?
It's not that hard. We have some people that have done that are early adopters of our production technology, that are basically venture-backed, high-performance companies with great management teams that are planning to make parts on scale. They don't use our technology just, but they use other people's technologies in the plastic space. That obviously happens whenever there's new technology. There's somebody that takes advantage of it and builds a business out of it. Our core business is really making equipment. So we don't want to be a service provider. We want to basically make machines to make people successful at making metal parts.
Yeah, so where are we going to be in 20 years?
So this is like the beginning of e-commerce right now. And then you look at 20 years, turn into a huge industry that were big. There's a few things that will be enabled by 3D printing at scale in mass production. So you're going to have mass customization, and you're going to have inventory of one. That'll finally become real, where a company might have huge warehouses today with 100,000 parts or 1 million parts. They'll be able to shrink that number of parts because they can always
have
demand digital capacity. Yeah, on demand. And that happened in books. Today you can publish a book and they print it on demand as demand happens, right? They don't store an inventory of books. They're printed with industrial inkjet. Same for tiles. So like people make the tiles, you wouldn't think that they're made with inkjet, but it's a huge business. So that'll happen with metal parts over the next 20 years. The next thing that's going to happen is I think you'll have borderless production will start to become more of a reality. A big company like GE might have 80 or more mega factories, and then they'll be able to do more final assembly in more locations as opposed to have centralized locations.
So more like distributed.
Yeah, distribute, and then you skip tariffs. You skip going through the border. You just send a digital file, and Then you can mass customize for the local market. Part consolidation, where you took 20, 30 parts and printed as a single component.
Describe that, because we haven't talked about that really much.
What Ric's describing is the ability to print one part that actually represents many, many parts. And so this is an example of a hinge that in reality would be like 3 parts, but that's printed as one part. That concept where you are really only producing different parts because you have to assemble them. That's a great example. Like, what function does that pin have in between the parts except to hold them all together just for assembly?
Another one is faster design iteration. If you're making a part that's created out of a casting process, you have all the tooling that you have to build. So there's a lot of overhead to change that design. You got to retool all your factories. Whereas if you're 3D printing them, you can change the design, and the next one that you print can be different.
And that's such a fundamental thing now in software. We take it for granted. The fact that you could do agile development, change your website anytime you want. It's a lot harder, obviously, in hardware.
The fact that you're toolless and you can create these parts without creating any tools for them opens up so many different doors. Okay, so if you have a change, you just make it in CAD and the next part you print is different. Well, the fact that you're toolless also opens up this door for this complex geometry. So complex geometry is now no longer a problem. And so it ripples through the entire process. And I think that over the next 10 years, we're going to find out even more about what a toolless design really enables. And one thing that Ric was talking about was artificial intelligence and machine learning. And I think that we're going to see these digital factories of the future evolve in a way that they could not evolve if they had relied on tools. What if you're producing parts and you notice the part is wrong and it measures incorrectly? You can design machine learning systems to pick up on that, to automatically change the CAD file and then immediately print something new and different. And it's not just if it's wrong, but what if you learn something down the road? What if the engineers are testing the parts and they've built 10,000 of them or 20,000 of them, and then something starts to fail and they say, oh my gosh, look at this little defect. Let's go back and look for it. And they go into the printer and they look for it and they find it. And they say, well, let's fix that. They can fix it in real time as the machine's running. And it's going to open up all these different possibilities.
From a design perspective, it's difficult to train people to know the intricacies of designing parts for traditional manufacturing techniques like casting, machining. What we're seeing here is we can build software now that encodes all the low-level rules for the constraints of manufacturing processes, and the software can generate these parts automatically to be optimized. And when you want to make a change to the constraints, you don't have to go through this whole channel of people to redesign everything manually.
I love how tools can enable someone with fewer skills to take part in that whole design process.
Tooling enabled the last industrial revolution. It's what allowed you to make parts cheaper at a given location and give it basically an intrinsic advantage. And once you made parts at that location cheaper, you would ship them all over the world. And that's where tariffs came from. So our whole global trade system was kind of enabled by tooling. And now we're going to remove tooling out of the equation. So it's a big change in the way we'll look at things over the next 100 years.
How's it going to impact American manufacturing?
It's going to shift the power to the designer. You shouldn't think about it as American. It should think about it as design. Look at a company like Apple. It's so innovative. They design everything in Cupertino, and then they do a lot of work around the world to make those products. And so design will matter more as you remove constraints to manufacture.
That's an exciting time for me, I think. I mean, having had a background in design, and that's where the human element comes, and understanding what the needs are, and the empathy and all that. You know,
an analogy is programming languages. You went back in the 60s, you had assembly, and then you had Pascal and COBOL and Fortran, and then you went to higher level languages like C, and then you went to object-oriented, where you took C as turned to C++, and then you went to like frameworks like Ruby and this and Python and all this. But the truth is that they're very easy to implement and more people have access to them. And generative design is like that. You just tell the computer what you need. You say, this is the mounting points for this bracket. Give me the most efficient shape. And you don't like worry with all this other crap that goes underneath it. And you get the part. and the part is better than anything you could have done by yourself as a human.
So now the engineering side of me is kind of like, well, wait a minute. Does that mean I'm like no longer
You're not.
needed?
You're going to be able to be more
Right.
productive. It's
Yeah.
productivity. This is, you think of what is productivity. This is productivity.
Well, and it's funny because I kind of purposely said American manufacturing, but I'm very much a proponent of local manufacturing because just creating those local ecosystems enables more creativity, collaboration, and all that. But I think that we definitely get very stuck in thinking, oh, productivity means fewer jobs. Well, no, you can actually do more with the same.
Totally.
Another aspect of this is, you look at the autonomous driving platforms that have evolved. Rick was talking about the evolution of programming languages, but there's been a recent one that's mind-blowing, and that is the software generating the software. And that's what's happening with the autonomous driving platforms. But also you hear about it with these games that are able to beat all of the known, Go or chess players in the world. And the latest thing is taking 2 copies of generative they call them generative adversarial networks. And what they are is 2 neural networks that are competing against each other to try to get better at something that they don't know anything about. And they are able to learn how to do something based on seeing the cause and effect reaction of doing something millions of times against an adversary.
It's kind of scary. I hope these networks have good manners when we start talking to them.
It does make me worried a little bit.
Yeah.
What was it? Was it the Twitter account that within 48 hours became racist?
It's crazy. Yeah.
Well, but even with live parts, for example, we have this crazy idea that we model the stress and the strain, right? And that feeds into the cells. Well, we have so many of these percolating in live parts that we don't know how to control these parameters. There's so many of them. And we're almost to the point now where we just want to wire it up to a neural network and let it start go off on its own until it finds combinations of these values that make sense, that make it grow better or grow stronger.
So it's not the designer anymore.
What we're doing is we're automating
Yeah.
the mechanism of finding patterns that work and then moving on those patterns.
It's actually really cool. But the other thing that it enables, it had never been done before, is design on a multiphysics context. So
Multiphysics.
So multiphysics design is a new concept where you basically have a part that is in the context of not just the mechanical loads, but also the thermal, the flow, so all these other things. And you can solve for the smallest part or the lightest or the most heat exchange in a space claim. So there are things that you could just never do as an engineer that now you'll be able to do going forward, which
So
is
there's
very
still
exciting.
jobs for engineers.
Yeah,
Right.
of course.
Well, that is actually a really good use case I don't think we mentioned, and that is using 3D printing to create parts that serve multiple functions. So you think of metal parts as typically just structural things that hold something together. But in mold making, the parts have to also cool the part that's being molded, like an injection molded part. There are people that are 3D printing the molds for other types of parts, like plastic or ceramic or whatever. But with 3D printing, they're able to print parts that serve 2 purposes. They serve the mechanical shape of the mold, but also they have these passageways inside them that you could never machine. And they're much more effective at removing the heat from the plastic or the ceramic that's being molded.
You have how many employees?
About 250.
And you said that they're all engineers, pretty much.
Most people are engineers. So the concept behind our company has been that our core competency is designing and innovating on the technology, and so we try to sell through a channel, and we try to make using CMs. So these are the other 2 functions that you would have had in a company. So that means that our function as a company is primarily built around our core competency, which is making the systems easy to use, making them user-friendly, making them do things that nobody else has made them do before. We enable a sales channel that's really, really good at selling this. So what we did to build that is we took the leading sales channel that sold plastic printers and the leading sales channel that sold CNC machines, and we mashed them up and we signed them exclusivity to do metal printers of this ilk. And today we have 84 partners in 42 countries. That gives us the ability to scale rapidly. And so it's kind of a strategy thing. Other people try to do everything themselves, and I think they can't be good at everything. So we know what we want to be good at, which is...
Could be challenging, though, I think, to maintain quality the feedback that you're getting from the customers, how do you take that feedback if it's not your team?
Well, that's where cloud software comes into play and our support staff comes into play. We can have a direct connection to customers even if we do it through our partners, our value-added resellers.
Awesome. You just raised another $65 million?
The company has raised $277 million
That's
since
crazy.
inception less than 3 years ago.
Wow. So what are you doing with all that money? You got some good parties?
No, we don't do that. We don't do that.
I don't see like a kitchen with all sorts. I don't see a lot of dogs. I don't see the snacks.
This is pretty Spartan. People are just doing work. We come 7 to 7, and we not entirely 7 days a week, but people work pretty hard and are motivated by the mission of the company and the culture of the company. We're just working and designing products. We're not doing cocomania parties or crazy stuff like in the 1990s. Yeah.
You make me laugh, Rick. So tell me about your 16-year-old self. I'm going to ask all three of you.
I don't know. I was from Venezuela. Grew
Yeah.
up in Venezuela.
So were you a nerd?
Yeah, definitely.
No.
Very nerdy. I really wanted to be in the tech business.
Yeah.
Yeah.
That's somewhat single-minded.
Yeah.
How about yourself, Andy?
I was the one that was usually trying to take things apart and figure out how they worked, and always screwing around in the garage building stuff. So I always had a history of doing things in the real world, and then I got sucked into doing software. And the reason I came here was because it was an opportunity to do software in the context of making real things. So,
How about you, Jenna?
So I grew up in West Virginia, and it was definitely a tinkerer and an engineer and a nerd, a math nerd. Certainly taking the lawnmower apart and turning it into a go-kart, anything that could really get me injured one way or the other. But in West Virginia, you could pretty much get away with anything.
Sort of last question is, if you had any sort of advice you wish you had when you were starting this business, or even just your first business, what advice would you give entrepreneurs that wanted to do some big stuff?
Dream big. Right now, there is no limit to the the ideas that are not crazy. I mean, the crazier the better. Right now, you as an entrepreneur, if you believe it, you can do it, and you can raise money for it. There's someone out there who wants to support you, and
I
your
don't really
crazy
believe
idea.
that.
It's true. There's a lot of venture capital out there looking for good entrepreneurs right now.
So what are the limitations, though? Are there
Well, I
ways?
think you're fighting with nature in hardware, so there are things that can't be done. We don't have levitating cars and things like that. But if you
Not
have,
yet.
I think that dreaming big is really good advice.
Any particular moment where you're like, oh my God, I wish I had not done that?
You design a product, and then there's always lessons learned. I want to do this differently. There's so many things we always want to do different the first time you do something, and then you do the second time, and then you do the third time, and you do the fourth time, the fifth time. So we have so many ideas for new projects, new products, new things that we think can make the world of 3D printing better.
I think another parting message that's important for entrepreneurs is there are not a lot of great new ideas, but there are a lot of great ideas that involve taking something from one space and applying it into a totally different area. We took metal injection molding material and processes for printing things like billboards, and you start mixing all of these ideas together and you get something new. Live parts is the idea of growing something like a plant to create a metal part. They're completely on the opposite ends of the spectrum, and yet it works. So you can generate a lot of interesting ideas by drawing analogies, looking at something that's successful in one application and applying it somewhere else.
I love that. That's awesome. How do people find more information?
On our website, at desktopmetal.com.
Any social media handles or anything?
Yep, at desktopmetal.
Check it out. I love hearing sort of the breakdown of what are some of the advantages, what are the real innovations that you're bringing forth, but also the future of what is this enabling? Because a lot of people talk about additive manufacturing, but most people's minds think of those stupid little bright green, lime green parts, plastic parts, right? You're really helping usher in a completely new future that people have been talking about for a long time, but haven't been here. So
Fantastic.
thanks for breaking it down for us.
Yeah,
It's
thank
been
you
fun.
for visiting.
I think the three most interesting lessons I learned today were, first, Desktop Metal's technology is faster, safer, and cheaper than other metal additive manufacturing like SLS and DLMS. But Rick made a really critical point. For 3D printing to really change the game, they aren't just competing against the state-of-the-art 3D printers. They need to compete against traditional manufacturing processes. On the tour, I saw their desktop models, which enable designers to get real metal parts without going to the machine shop. And I had a chance to see their new production system, this huge machine, which is coming out early next year and will be cheaper than machining and metal casting up to 100,000 units. Second, I like how Desktop Metal recognized the opportunities unleashed by 3D printing and jumped right in to create the new design tools to take advantage of them. Andy's tool, called Live Parts, makes it easy to design parts that are much more organic. It's a process called Generative Design. And what's especially cool is how you don't have to have engineering skills. Instead of guessing and telling the system where to put metal and then analyze how well it's doing, you tell it certain constraints and then the software figures it out. It's only recently, with new computing power, that these kinds of parts can be digitally grown in real time. If you want to see a video of Live Parts software in action, check out the show notes online at makeitinla.org/desktopmetal. And finally, production 3D printing has the potential to completely change so many things about our industry today, even beyond what we can build. Cost of production will go down. Parts will be consolidated, which means assembly will be simpler and labor costs can be reduced. Complex geometries will be possible with less material, including multi-physics designs. For example, you can create a radiator that combines fluid flow, structural strength, and the thermodynamic functions in one part. What happens when products can be shipped around the world like bits instead of atoms? Manufacturing can be distributed and localized. Tariffs might not make as much sense. And we didn't talk about this, but intellectual property protection might look a little bit different too. And imagine if there's no expensive tooling. Designs can be iterated on much more rapidly, and machine learning can help evolve the products. Mass customization will come standard, and companies won't have to keep inventory. We actually saw some of that already happening in episode 44 with Weave. And localized manufacturing and simpler parts also means greater sustainability and less impact on our environment. The future people have been talking about is right on the horizon, and it'll be fascinating to see how it all unfolds. Are you using 3D printing in your company? I'm curious, how is it changing the way you do business? Let me know. Email us at team@artofmfg.com or message us on social at artofmfg. Time to wrap it up for the Art of Manufacturing. Tune in next Thursday when we meet another inspiring founder taking on their next big venture. In the meantime, did you like the episode? You made it this far, so I bet you did. Do us a favor, please, and tell your friends so we can grow and continue to bring you great content. For show notes, visit www.artofmfg.com. Follow our adventures on Instagram and Twitter at artofmfg. And to chat with other like-minded creators, join the Art of Manufacturing Facebook group. Never miss an episode. Subscribe on iTunes or Spotify or your favorite player. And if you like the show, do us a favor and leave us a review. Or send us a message with your thoughts and ideas to feedback@artofmfg.com. This podcast is produced by At Large and Dangerous in collaboration with Make It in LA and other partners. Visit makeitinla.org/connect to sign up for local LA events and news. A big shout out to Peter Brandenburg, the producer and audio engineer. Thanks for listening to The Art of Manufacturing. I'm Z Holly, and remember, don't just make it, make it.